So I'm delighted to introduce a good friend of mine, Professor Shafer Smith. Shafer is visiting us from New York University, where he is a professor of mathematics and ocean and atmospheric science. And we probably met 20 years ago as postdocs. So Shafer did a dual major physics and mathematics degree at University of Santa Cruz in California. That was undergraduate, I'm sorry, in Indiana University. And then he did a PhD in physics at the University of Santa Cruz in California, where he worked with Jeff Barlis, who some of you might know because he wrote a pretty big textbook on geophysical fluid dynamics that many of us have been reading. Shafer's research interest is large-scale turbulence. So, and you know, some of you may know him personally, some of you may know him through some of his papers. One of my favorites is Smith and Ferrari from 2009, where Shafer showed that if you look at mesoscale strain and stress, that you can predict the kind of aspect ratio of filamentation in the ocean, which is really cool because if you look at CTD data a lot, like I do, you can see these sorts of structures in the ocean. So without further ado, thank you for coming, Shafer. The weather's definitely cooperating. And today it's going to talk about sensing submesoscale structures from SWOT.
Thank you very much, Lisa, and everybody. And I see a small audience, small group of people. If I was teaching a class, I would definitely encourage everybody to come forward and stop me and ask a lot of questions, and not let me just go on if you don't catch something. More fun if it's interactive, and I don't get to do that, and that's okay. First of all, the title, I attempted to be a little cute, alliteration, so really, that's a better title. Apologies for that. But this is what we're really trying to do, is figure out particularly how do we extract the transport active part of the velocity field from SWOT, and I'll get to why that's a question at all. First of all, a bunch of collaborators, so I've been funded by NASA on the science team for a few iterations. In the beginning, it was with Ryan Abernathy, and eventually Joe Balwada as a first postdoc, and then Spencer Jones as another postdoc, and they're both professors now, respectively, at Columbia and Texas A&M. Chino was a PhD student, so a lot of the stuff I'll show is his work. Ryan Abernathy was my co-PI at Columbia, who now started his own company called Earth Mover, kind of leveraging all this stuff that he developed with Pangeo and stuff into big data services for Earth-centered companies. So he's gone. I've faded them out there with the images, so you can see. Ryan is slightly faded at 80% there because he's about to graduate, and I won't really talk much about his work. And then there's three new people in the newest science team who got funded: Leah Johnson, APL, and Abigail Bogner at MIT. Tatsu Monkman is a postdoc who just started with me at NYU. He's done a bunch of stuff that I won't really get to. So there's a bunch of things I'm going to talk about. I should say that before I advance about SWOT, and I'm going to focus on a lot of stuff that doesn't actually. Most of it's not actually using the satellite data yet, and it's all about the development of the kind of ideas we're trying to use to get what we want from SWOT observations. But to start with, in case you don't know what SWOT is, or even if you do, I might focus on some parts that you don't know. So it's an interferometer. It's a new satellite buzzing around near polar orbit, and so it sweeps out over the course of about 21 days, covers most of the globe, the oceans. It differs from traditional satellite altimeters. Is my sound okay and everything? Yeah, okay. By technology. In that the original altimeters send a single beam of light down in a track following their path, and so you get very high resolution along track. But by the time the Earth rotates under and it gets another track around, you're about 100 kilometers away from the first track. So you have very discordant resolution along track and across track. And when you remap to make a field of SSH for the ocean, sea surface height, You end up with an effective resolution of maybe 50 to 100 kilometers. There's multiple traditional meter altimeters right now, so you can get something like that. And there's nice advances there, but the kind of positive part of that, in a way, that low resolution is that when you're at those scales, 50, 100 kilometers, the flow, the surface of the ocean is very much in geostrophic balance. And so it means that a little work and a little subtraction of geoids and time averaging, you can take a couple first derivatives of that remapped flow and get a good estimate of the horizontal lateral velocities in the upper ocean. Okay, so what's special about this satellite is it's not just measuring long track, but it's measuring simultaneously two swaths of sea surface height that are about 50 kilometers wide, each one of them. There's about a 20-kilometer gap, and there's also a nadir altimeter in the middle. And so it's mainly, so the science team for the oceanographic part and learning things about the ocean is, if it's this unit, there's about twice as many people in the science team for the hydrological applications of SWOT. And so there was a kind of conflict in, not in a negative sense, but differing desires for what it's going to be used for. And in the end, so for oceanography, we would have liked a repeat phase that gave us more rapid repeats of the ocean, something like 10 days. It's 21 days in part because of the need to spend more time. I'm not sure I understand some things about why the orbit was set that way, but at the end of the day, maybe I should stick with this, is that you get basically a snapshot of some region of the ocean, and you don't get another snapshot in that region for another 21 days. So that's an extremely long time, even for mesoscale eddies. That's pretty long. Things have moved on, especially for faster scale submesoscale things, and certainly for waves now appear like they're completely alias, which I'll get to. There's a lot of waves in this here. Okay. Cute little image that I stole from NASA to give you an idea of what it looks like over a nice 3D picture of what those tracks look like, and that's focusing both on its uses for measuring the ocean and hydrographic land. So the cool thing is it had a certain design specification, engineering guidelines that it was intended to beat, and it was over-engineered. So in fact, the satellite is producing and seeing much finer scales than even people hoped for. And so for a long time, and having gone to the science team meetings for years, there was a period, sort of 2017, 2018, W. Sheldon gave a talk, and it sort of looked like, yeah, what you're going to get at is going to be kind of crappy, and it's going to be a better kind of mesoscale altimeter. We won't see any submesoscale stuff. But in fact, it's actually beat all these expectations by a lot. So this is from a paper, a preprint. I think it's now published in GRL by Archer, Wang, Klein, and Fu. So it's kind of a couple showcase observations from SWOT. It's a showcase paper, but it's nice to look at these two images. So there's one taken in the Indian Ocean. You can see in the upper up there, a little block. That's this cutout here. In the background, you have the kind of traditional sea surface height measurement that you get from DUACs, so taking a bunch of nadir altimeters, remapping, very fuzzy. Here's what you see with SWOT. And in this particular case, they cherry pick some nice examples. You see actual kind of large scale wave crests here. So this is like 14 south, 13 south, so that's maybe 100 kilometers there. And you zoom in on this thing, which is maybe 50 kilometers, and you can see these wave crests across. But if you look along there, you also see a bunch of little wave crests going along the bigger wave crest. Those features have wavelengths of about, those are swell, and they have wavelengths of about 350 meters. So you don't always see things this clearly. And we have been looking at the data with the postdoc, and they did have to work a little bit to pick a nice example here, but in many places, in many cases, you will see extraordinarily finely detailed structures in this data. Very cool. One more example, also from the same paper, just focusing on something more, it's a wave feature, and gives more of a balanced feature, is a very strong vortex here. It's about a quarter of 15 kilometers. And you can see if you looked in the background flow, this is the sort of image you get from the best product we have for traditional altimeters. And as you can see all of a sudden a lot more detail about what's going on. So And also, so this is 34 south, 15 kilometers. This is quite a bit below deformation radius there. And this flows, you start to, those scales, I'll get into this, you start to see some pretty strong asymmetries in vortices, and these things get up to order 1 Rossby number, which is the issues here. Okay? So the great thing is, yeah, so SWOT seeing features at smaller scales than expected, but the problem is that, of course, these motions in both examples are, especially the first one, are not geostrophic. All the wave stuff is obviously completely ageostrophic. And that means that once you lose geostrophy, which we kind of had as a side benefit from the low resolution remapped traditional altimeters, you don't have an easy way to get the velocities. And so there's many possible uses for SWOT, and there's many things people want. Our particular focus has been how can we make a better mathematical or machine learning model to get specifically the part of the velocity field that is active in transport. So I'll try to say what that means here in a little schematic. You might think of the surface velocity defined at some kind of, depth where that's consistent with the hydrostatic pressure from the sea surface height. So where the part of the flow might be due to geostrophy from the sea surface height. And you can think about the 2 geostrophic parts there, and if I only had kind of large chunky scales, that's going to be about all I need. So you go to higher scales, in fact, the real velocity flow, if you think about U surface being the velocity of the actual ocean, and there's many things going on, you can decompose it into some other parts. And you might include also now an ageostrophic balanced part. And by that I mean things like strong fronts undergoing frontogenesis, strong cyclones that are stronger. So at the QG geostrophic scales, you have rough symmetry between cyclones and anticyclones. Once you get to higher Rossby number, you start to get stronger cyclones typically. So for example, you might learn about cyclogeostrophic balance, which takes into account the centripetal force going with a little bit of a strong vortex. But yeah, those are non-geostrophic terms. And then on top of that, of course, there's wave motions. There's many kinds of internal wave motions. There's, of course, the swell. There's inertial oscillations that start to get modulated by the eddy field. And there is the baroclinic tide. The baroclinic tide in particular, so sloshing over from tide, sloshing over topography, generating barotropic tide. Once it converts to baroclinic tide, and then these motions, some part of them, have very similar scales to the kind of submesoscale features we want to see, but time scale is much faster. So they're completely aliased onto the field. If you think about these guys whizzing around quite fast compared to submesoscales, and you take the snapshot and you don't get another one for 21 days, you cannot hope to use any temporal information or time averaging to get rid of that part of the wave motion. So this is a pretty big problem then, right? You can imagine. Okay. So the other part of this is the first 2 things. The geostrophic, we know lots about geostrophic flows. They transport stuff. What I call balanced ageostrophic, which is an imperfect term because it's not, what the definition of balance is tricky. But let's just use that as a term of art for the moment. What I mean by that is all this stuff that is not in geostrophic balance, but that is moving things around. So think about the front. So when a front forms in the atmosphere at the surface or in the upper ocean, typically have strong convergence in the ocean, and then you have a fascinating feature where you get an ageostrophic flow that reinforces the front, and it gets very small and very intense very quickly relative to what you would compute from background strains alone. And along with that, you get very strong vertical velocities. And these vertical velocities that form at fronts and filaments in the ocean play a significant role in the vertical transport of the ocean. So for example, those fronts are removing and taking down a lot, pushing a lot of the anthropogenic carbon that sits near the ocean surface and pushing it down through the mixed layer into the deep ocean. You get stronger downward velocities than upward velocities in fronts, but the upward velocities associated are also bringing up nutrients in the winter and driving phytoplankton blooms. So a lot of stuff going on, not geostrophic. And then there are these strong vortices. In some ways, the fronts are kind of the thing we really care about, because they're associated with this strong vertical transport, making that a zeroth order of the thing. You know, if you're an atmospheric modeler, climate modeler, and we focus on the ocean. If you're a climate modeler, often, the ocean, you'd like to think of it as just a slab and a thing that takes stuff up and sucks stuff out of the climate. And so, but even then, if you're going to get, you got to get this part right, how much it takes up. So it augurs for trying to understand this part of the flow.
Okay.
Yes.
So one word you haven't used is gradient, like gradient balance.
Cyclostrophic balance is gradient, yeah.
Well, okay. I mean, I would think gradient balance is like a mix, right? Cyclostrophic balance and geostrophic balance. I'm just wondering if you're not using that word intentionally. When you say balanced aid geostrophic, when I think of like a strong vortex, right, then the more accurate velocity would come from a gradient imbalance.
Yeah.
So
I'm not distinguishing that. I'm not trying to avoid any particular words. I'm only saying, even in that language, you're thinking about stuff that's not wave, right? And it's not geostrophic. So anything in that category that's not like an inertia-gravity wave and not geostrophically balanced, I'm putting in this broad category. That's why I'm trying. It's a slippery word, and if somebody knows a lot about balanced stuff, then I get into trouble. But
in that category, there's still divergent and non-divergent.
That's right.
So the fronts, you would have convergence.
That's exactly the problem, right? Is of course, when we think about, some people, depending on how much GFT you've done, you might think, right, the geostrophic flow has no divergence and the waves have no vorticity. Neither of those things is true.
Sure.
The internal waves have vorticity, and the balanced stuff does have some divergence, right, and convergence. It's just that the convergence you get on the scales of vortices and fronts is not the beta-driven thing at large scale. It's from the fact that you have non-linear, non-geostrophic stuff coming into play. Gradient, wind balance, cyclostrophic balance. I don't distinguish those too much, but fronts are certainly something different than that too.
Right.
So, okay, is that cool?
Yeah.
Is your discussion focused on oceanic fronts, or will you be talking about like coupling between atmospheric fronts?
I'm just focusing on the ocean part. So my limited goal here is to tell you some background stories about specifically how we're trying to get these velocities from SWOT observations. Many other interesting things to do. And the air-sea coupling part and what happens to submesoscale stuff is a big thing. There's a new simulation, COAS, that's high resolution atmosphere and ocean coupled, and not what I'll talk about. Okay, so the other part about this stuff is that stuff, the fronts and the geostrophic achieve transport. The waves do not. So the internal waves to first order and beyond wiggle things around, and unless you have them coupled with some diabatic effect or something, they are very ineffectual at transporting stuff up and down, tracers, heat, oxygen, carbon, etc. And the fact is, we not only want to get the middle thing, we want to filter out the thing on the right, and yet we don't have a mathematical model for either of those really, and so we're this is the challenge. Okay. All right, so I'll go quickly through this. This is just to remind me to tell you that there's a bunch of background papers involved in this, which I'll kind of go through. That's going to be partly about a statistical method for how we see what flux is being accomplished by which parts of the flow, how we can figure out what the wave part is, how we can extract the transport, how we can create a truth simulation. I think you'll see this as I go along. Let me just go to the pictures and keep one. Okay, so this is, the color is different on the screen. This is from a paper to start with in 2018, Belawada, Smith, and Abernathy. It was specifically, so it's a channel simulation, MIT GCM, 3 kilometers deep, 2,000 kilometers square, winds and temperature forcing across the top, no seasonality. There's a ridge in the middle to give you some inhomogeneity, all that stuff. Classic setup. The specific thing we were trying to do, and then we put a tracer in at the top that is driven by very fast restoring right in the first 5 meters to some background value. And then we run this simulation at 3 different horizontal resolutions. So the deformation radius in that flow with the stratification there is maybe 20, 30 kilometers. So the resolutions are at the top for 3, and I'll tell you what those pictures are in a second, but there's a 20 kilometer, 5 kilometer, and a 1 kilometer simulation. So everything's the same, the forcing's the same, tracer input's the same, and we're asking simply, very straightforward question, which is, as I increase the resolution and start to introduce submesoscale stuff, whatever that is, does it change the vertical transport of the tracer? Does it increase the rate at which it's drawn down from the surface into the interior? Those pictures there, the color is very washed out. You can't quite see. If you're looking at my screen, you will see. So there's the tracer. You can think of it as max being 1, and this is these are snapshots of the tracer at the same relative time for each simulation, 1 model year after you start putting the tracer into the surface. And the depth is at the mixed layer depth plus 100 meters. The mixed layer depth changes in these simulations because once I get to very high resolution, like 1 kilometer, you start to get things like mixed layer instability, which is a submesoscale, little mixed layer scale instability, baroclinic instability. So if you know the ED model, it's like a little ED model, only the deformation radius is like a kilometer, because if you take mixed layer depth of 100 meters and N in the mixed layer and F, you get about, 1 kilometer. I didn't say it, I meant 1 kilometer. So anyway, there's a new resident thing there, and that thing tends to shallow the mixed layer. So we thought a fair test is to look some depth below the mixed layer, because we're particularly interested in how much vertical transport, extra transport happens that brings more tracer below the mixed layer and into the interior. So on the screen, you would see that there's a lot more here after a year than here. And the paper has better diagnostics. It was supposed to just give you kind of a visual idea. We find basically there's a lot more accumulation of tracer at depth as a function of time when you start to introduce these submesoscale things. So you could I've got a bunch of papers to talk about, so I didn't show much here. So the question then is, you could say, well, okay, you introduce submesoscales. We know that introducing submesoscales changes some large-scale features. It changes the depth of the mixed layer. In fact, it's making it more stratified. So you might have thought increasing resolution, introducing submesoscale, introducing new restratifying effects in the mixed layer might suppress the vertical transport. But you're also introducing a lot more kind of turbulence and kinetic energy and stuff that may be affected or going down. So that was one question. The other question was, it might change large-scale mean structure. So basically the question is, that extra transport, is it due to kind of effects on the large scale, or is it really due to the plethora of new little features you've introduced? And then you're stuck with, like, how do I figure out, how do I tell that apart? So I'm going to tell you about a statistical method that's kind of the core idea of a lot of the stuff we've done in a minute. First one to say, this was a little bit out of place, I had to show the simulation first, so just wanted to say when I make the claim, color is, okay. So to explain my claim that stuff is not very geostrophic. So from those same simulations, there's a little cutout of it. There is, I'm showing the vorticity divided by F. Here is, say, the actual vorticity in this 5 kilometer simulation. And there's the geostrophic version of vorticity at 5 kilometers. And actually, they look pretty similar even at 5 kilometers. Once you go to the 1 kilometer vorticity and the geostrophic calculation for the 1 kilometer simulation, you start to see that there's a big difference in that by computing just the geostrophic estimate, you actually introduce a bunch of noise, because you're taking a derivative of a flow that has a bunch of other stuff going on. Note also in the simulation, the forcing was steady. There's no tides, there's no direct introduction, there's no high frequency winds, there's nothing intended to excite inertia-gravity waves. You do still get some at 1 kilometer resolution, because there's spontaneous generation of Rossby waves, gravity waves. They're still pretty weak relative to cases where, other simulations I'll talk about where, you're really trying to inject wave energy too. Some of that is the fact that the pressure field has waves in it. This diagnostic, which I'm going to tell you about in a minute, more about, is a joint probability distribution of vorticity and strain. I'll tell you what that is in a minute. And the main idea here is you can see that if I compute the truth or the geostrophic estimate for 5 kilometers where it looked okay by this analysis, when you look at the PDF, they look more different. Once you get to 1 kilometer, they look quite different. Maybe just hold that picture in mind that the geostrophic calculation for the high resolution looks very different than this, and I'll get more into what those pictures mean. Yep.
So from over here, those upper two panels look basically identical, except that...
I feel like you should come look at my screen, because the colors are really washed.
Well, the big blue river at the top, they differ on a 50 kilometer wide big blue river.
That's true. Why do we care, right? So I'll try to get to this in the next few plots, but in fact, the small scale stuff that you're missing, I mean, even actually look at the axes there, what I chose to look at. That's 500 kilometers.
Yeah.
So even though at 1 kilometer, this stuff from 1 kilometer, well, the dissipation scales, maybe say 3 kilometers up to the full scale. So the big scale features you probably are going to get right. It's specifically the introduction of that smaller scales dynamics that is where things start to go wrong. So in some sense, maybe I should have had a little microscope view to look specifically at the new scales I'm going to introduce, but then the larger scale stuff would look stupid and boring, right? So
isn't the big blue U there at the top, isn't that probably some big geostrophic current?
it is, yeah, but it's at the
So why
scale.
does it differ from geostrophy and truth? Why are geostrophy and truth so different on a very large scale blue U-shaped thing?
Well, they're pretty similar in that large scale blue U thing, right? I'm saying the difference is in the small scale stuff that you're introducing. You can see maybe there's, I don't know if you can see that, well, there's a whole bunch of little bumps every place all over here. And so in some ways, actually, the problem maybe you're having looking at the upper case, this is one of the reasons to start to look at things in the statistical way instead. How do we break things about? So if you just trust me for a moment, if you don't know, have not seen a plot like this, and most people haven't, this many people have even a PDF and something like this in 1 dimension. And if you compress this, if you just send a sum in that direction, and think of this as a PDF in vorticity, you'll already see that in this 1 kilometer case, it's going to be very asymmetric in vorticity. There's a lot more cyclonic stuff than anti-cyclonic stuff. This weird shape, I'll spend a lot of time talking about. The main thing is to look at the difference between this and this. If you look at, like, say, all there, and all here, now I've got, what is all this stuff? That is not in the flow at all. So it's all noise. It's all incorrect, right? So because with the truth, the advantage of using a numerical simulation, I have access to everything, right? So I can play games like that and cut things out. Yeah.
Are the colors plotted at the top vorticity over F, or is that wind speed?
It's vorticity over F. Yes. Yeah. Okay, let me go on because I think maybe this will get more clear. So the next thing I'm going to tell you is that this approach to looking at flows. So we don't know exactly which part of the flow is causing additional vertical transport. So this is an idea that came primarily from the first place we saw this kind of distributional view is in this paper by Shafer et al. 2013, which was part of the Latmix experiment. Maybe some people know about that. And that experiment is one of the things they did in March 2012. They took 2 ships and drove them parallel to each other so they could make kind of vorticity calculations by taking derivatives across these tracks. But there was also a big modeling simulation and all that stuff. Anyway, they we saw some of these vorticity strain PDFs, and I'll get to it. Okay, let me continue here. But what are the vorticity, strain, and divergence? So vorticity, we're just thinking about horizontal because we're thinking about surface stuff. And so the vorticity is that. The divergence, the horizontal divergence is this. That's just the sum du dx, dv, dy. The strain, so if you know this stuff, if I think of making a little strain matrix with du dx, du dy, dv dx, dv dy, I can take eigenvalues and eigenvectors, that stuff, and the first thing you do is to rearrange that in terms of vorticity and divergence and 2 strain components that are the other 2 combinations of the first derivative. The vorticity and the divergence are independent in coordinate. The strain components are not, but if you take the sum of the squares of them, then you get something that's also coordinate independent. So you might think of these as three good measures of kind of the first derivatives of the flow, and that we can associate some stuff with. And vorticity you're used to looking at. Strain, you'll tend to pick out kind of features where there's strong lateral shears. And then the divergence, of course, where things are pushing together or pulling apart, which is always going to be associated with vertical velocities. Okay, so if I now take those three fields and I simply bin them together, I make a histogram, and then normalize it, I get one of these joint PDFs. So from that same flow, this is the vorticity versus the strain. So that strain, it was the sum of the squares and square roots, so it's only positive. The vorticity can be positive or negative. If I'm in the southern hemisphere, F is negative, either way. And when vorticity is the same sign as F, we call that cyclonic. And anticyclonic would be the negative vorticity part. And this is then, so it's really, we made a 3D joint PDF in terms of the vorticity, the strain, and this horizontal divergence. Ideally, you have like a big 3D picture, but that's really hard to visualize and plot, so we do it in two parts. So we think of vorticity and strain, and this is vorticity and divergence. And you're going to get a better idea in the next few slides about how to look at this. Why do we see the features we see, which you might see, just for starters, the vorticity asymmetry, the fact that there seems to be a whole lot of stuff that moves to high vorticity and high strain values along this line of strain and positive vorticity. A little bit there, but not much. And that the anticyclonic part kind of gets cut off, and the cyclonic part would seem to go to much larger Rossby numbers. And that the divergence tends to be, so negative divergence is convergent, stuff pushing together, like fronts. So the fact that it's more negative than positive is consistent with there being fronts. And they seem to be correlated also with positive vorticity. So let's see more about what's going on there. I guess I said all that. Yeah. Okay. So this is a little explainer for what's going on there. So now we take just a little snapshot from that. This is the whole flow, the 2,000 by 2,000 kilometer domain, 1 kilometer resolution. Take a little close-up of a particular feature here that's kind of got a big anticyclonic swirl and a bunch of little strong cyclonic vortices. So you can already see some of the asymmetry there that you get and that's what you tend to get and start to resolve submesoscales as much stronger, smaller vortices, cyclones than anticyclones. And then I can make the same PDF from that, so there's not much statistics. It's one snapshot, one little area, but I can still bin the vorticity and strain from that little feature on the right. And you see the same, qualitatively the same kind of shape. So then what you can do, if you save all the information when you make this histogram, I save all the data about exactly what part of the flow it came from. Now I can go to the statistical view and I can cut out everything except for the lower triangle, and then map that back onto the same space. And what you'll see is the part down there kind of picks out the big anticyclonic swirl. The part under the cyclonic, so AC anticyclonic, C cyclonic. The part under the other triangle, you end up just picking out the little cyclonic vortices. And then the stuff up there, you end up picking out all the kind of fronty stuff that's between them. Okay. If anybody's really interested in this stuff, please look at the paper or my slides, run one so you can see the better colors, and I'm happy to show you a little more impressive here. So that's the basic idea. This stuff, one for one, helps us separate kind of flow features statistically. The other thing is, so why is it that if that front stuff is above, and why is there this asymmetry? And I'm not going to give you a complete story here, but let me just show you part of it. You might think, suppose I have a front going in one direction, so like in the y direction, right? So the vorticity of that front then is just due to the x derivative of the north-south flow, so dv dx. I only have one component. And the strain turns out you can write this, and so the only divergence I'll have there too, if I have a long straight front in the y direction, is stuff moving in or out in the east-west zonal velocity. So du dx and dv dx are all I have, and the strain is then going to be the sum of the squares of those, which is the sum of the squares of the vorticity and the divergence. And that tends to be always greater than or equal to vorticity. And why is it not much bigger? It's because for these fronts, you tend to have much smaller divergence than vorticity. The divergence adds a little bit, but most of that fronty stuff, if I didn't have any divergence, it would be exactly on the line, exactly on the line. Was there one more part there? Very close to, vorticity. Oh, right, I guess. Very close to sigma like vorticity.
Shafer, so
Yes.
in this example, you're stipulating there's frontogenesis. Right. You're saying that the large scale, the flow around is frontogenic. It's not coming from the current.
Right now I'm just telling you a cartoon about fronts, and not necessarily large scale. I'm actually thinking about, well, we'll see the scale. In fact, okay, what's over here on the right? This is just a little part of the flow, and this is, that's plan view. You can see a front and temperature there, right? And this is now vertical view going across it. So you can see a nice little outcrop. W you can actually kind of cool. You can see the strong features there. This higher frequency W stuff is the bit of wave stuff that shows up. If you now look again in plan view along that front, you'll see that there's a very strong positive vorticity side and a weaker negative vorticity side, and strong strain that goes along with that. And that when you now just plot, that same plot for that one little front, one little segment of the front, you see that almost all those points lie on this vorticity equals strain goes like the positive vorticity side. Okay. So that's all to argue that if you find a front like this, that's where it shows up in the statistical view. That makes sense, right? So then the question is, okay, so feature identification method, now we can ask how much of it's this front, and the other part is it's going to be what's the scale, because you implied that too. So I get one more thing before I get to that part. So hard to look at both divergence, all of vorticity, divergence, and strain together. This was Ryan Abernathy's killer idea, is to say, well, let's bin the divergence in the vorticity strain. So now you condition, for each point, you compute, the four derivatives, and you can compute the strain, the vorticity and stuff, and the divergence. Now I can make that PDF, and I can say in that one point, how much divergence is in all those points that have that strain vorticity value. So what you see here is that the blue is negative, so that's convergence, right? So this is also showing you that all of this, what you should see here is that I have high positive vorticity, high strain, and negative divergence or convergence. It all tends to lie just above this line, so consistent with having a little bit of non-zero divergence, because that's what brought it up above vorticity. And that it tends to all be, convergent. And what you need is, if it's fronts, a real front, if I have divergence, if I start to have a temperature front here, and I somehow have divergence, that's going to rip the front apart. That's frontolytic. A real frontogenesis, so fronts that are undergoing frontogenesis, it means that there has to be a strong convergent velocity pushing it together, making it tighter, and then it gets this amplification from the process of frontogenesis. But so this is telling you that this what we're seeing there is a bunch of strong convergent fronts all over the flow. The last part of this is about the scale. How do I know what scale is happening at? So this is now again the 1 kilometer, 5 kilometer, and 20 kilometer simulation. The full flow, that's the vorticity there. And I'm going to show, maybe start from the 20 kilometer here. So I make the joint PDF of vorticity and strain. And there's some, if on the plot, you might see that's darker there, a little bit lighter, and a little bit lighter here, and there's kind of self-similar contours to that. And you can see the axis here is -1 to 1. So in the 20 kilometer flow, everything is kind of still smallish Rossby number, right? The tails are out here at 1/2. Most stuff is in here about 0.1, right? So it's very, and it's kind of symmetric, closer to symmetric. So, right? So you have limited strain, everything's less than 1. 5 kilometer, now you get a little bit bigger. Now the axis is 3 times larger there, right? And you get, it starts to get more asymmetric, and so higher Rossby number. And so there's a feature you can't see on the screen here, which is I've put this outer contour is actually in there, and it fits right in there in the inner part. And then we go one more level up to 1 kilometer, and now the axes go up to 7.5, plus or minus 7.5, and 7 up there. So it's gotten, so this whole feature there, that contour is right there. It's kind of overlaid in here. So what I'm trying to get across is that as I increase the resolution, you get this kind of self-similar, almost self-similar change, right? So as I introduce smaller scales, the extents get larger, the extent of Rossby vorticity and strain, and all those new scales that you're admitting are going into these higher strain, higher vorticity values. So what this is telling you is that you're actually also getting scale from this. It's the indication is that that's the same plot that I showed before. There's you can see those contours a little bit better. So this is now the same thing, only actually this is now this tracer flux from below the mixed layer binned by this. So it's you get that from this convergence. But what you'll see is you can see this contour there. You can kind of see it there, and that little one is there. And the next one is there, and then there's getting everything there, right? So everything sort of between this outer contour and there is from these new smaller scale features. There's a better way to do this in the paper that's more kind of quantitative, but there's a lot of very strong indication that those extra features are from the increased resolution. We also did something where to kind of show this, if I take, which thing am I doing here? This is, if I take the 1 kilometer results and I smooth them out, I coarse them down to 5 kilometers and make the same statistical calculation. In fact, all that stuff ends up in that inner contour. Does that make sense? So I'm asking the question, it's not necessarily, in fact, literally if I take the high resolution flow and I just smooth it a little bit down to 5 kilometer, in fact, it's just cutting out those small scales in this self-similar way in this plot. So we have like feature and scale by this analysis. Yeah. Okay, so that's the first part. Hopefully got those 2 bullet points straight. That's the idea of this method is how we can separate out what's going on. And it's showing that in the first simulation I talked about from this 2018 paper, and this stuff is from this 2021 paper, also led by Drew Palwada, that in fact with the statistical method we can infer that it is specifically small scale, mostly small scale fronts that are actually increasing this vertical transport downwards. And when we increase the resolution, all that extra transport is happening sort of in these there's those inner contours there too. That a lot of that extra transport happening at the highest resolution is all this stuff out here, all that blue part outside there is new vertical transport. Divergence here, vertical transport of tracer will be similar picture. So we've learned something from this method, that in fact it's important that you get all these small scale rapidly forming fronts to get the vertical transport right. So there's that tells us how to look at what's going on in the flow. It doesn't tell us anything about how to figure out what the velocities are. So the next step is going to be to, let me take an aside here and say, you might think, in that simulation, almost wave-free, there's some wave stuff that shows up and it's a problem. There's fronts, clearly, and there's strong vortices. You may know that there are other kinds of models beyond QG or geostrophy that will give you some of that. And that's another part of work of our efforts that I'm not going to show, is kind of using a higher order balanced model to try to directly infer from a direct deterministic mathematical formula. You give me SSH and maybe sea surface temperature, and I tell you what the surface and flow just below the surface is. There's a whole part of the literature that's devoted to this. There's these methods called the ESQG method that's about using surface quasi-geostrophic approximation, and it allows you to do something like that. It doesn't get the submesoscale part, it'll get part of it. We're trying to do something that gets a little bit better. Another way to do that is to say, okay, I know there's this other stuff in there I want to get, and I don't know the mathematical formula for it, but I've got a simulation where I know the truth that I want, and I've got the thing that I measure, and I can ask, can I train a neural network to infer these patterns? So,
Can I ask one question
Yes.
before you go on?
Yeah.
Because it's about the last part. So the blue stuff, that's from
right here.
the long skinny fronts, right?
Yeah, and in fact,
So that's
there's many kind of.
So is it right to interpret that that's kind of mesoscale stirring rather than submesoscale vortices?
Oh, right. So the thing is, right, whatever generates the fronts. Yeah, maybe this is bigger. Maybe it should be bigger. But this is the whole domain. You can see that topographic feature there. And this is the divergence I'm looking at. So the negative part is convergence. So, you can see that they're strung out over long space, right? And if I have, in the low resolution case, what pictures I have from you don't really see it there. If I looked at the similar picture of the low resolution case, you'll still see some kind of asymmetric front-like things, but they don't get very strong. They don't undergo real frontogenesis. So if I have high resolution, what makes those little fronts? So the fronts we can see that we're getting new fronts that are very small, very intense, that are pushing stuff down. But what generates them is what you're asking about. Indeed, you still need mesoscale strain to generate them. Now there's papers about this too, about whether it's mesoscale strain or there's this whole idea called turbulent thermal wind balance from the Williams group, which is I won't try to explain, but there's some a couple ideas about what's generating the fronts themselves, but indeed, you do need those mesoscales to get the front regeneration. But if you have a low resolution simulation, even having the mesoscale strain isn't going to give it to you because you can't resolve.
Yeah, I get that part.
Okay.
Okay. It's better. So a lot of it is better resolution of mesoscale stirring or filamentation or whatever you want to call that. But the frontogenesis is potentially more by the mesoscale than the submesoscale.
It's generated by the mesoscale, but you won't get it unless you have small scale resolution.
Yeah.
So these small scale features, if I say, took the 1 kilometer simulation and turned off the winds, so I don't get any geostrophic, large scale baroclinic instability. I'd start some kind of initial value problem, something like that. You won't get as many fronts. Okay. So the learning part of this, so I won't spend a long time on this, but to give you the big idea. So first try to basically do a neural network on the same simulation to say, can we learn, see the SSH? So you say from the model, I only let the neural network see the SSH and ask, can I predict actually the vorticity and strain? So we've specifically kind of skipped over predicting just the velocity itself and gone straight to predicting the derivatives of the velocity, which has some advantages for making sure the network, once you try to learn something and you get the field and then you take a derivative of it, you're more likely to get noise. But if you train it on the derivatives, you're likely to get something a bit better. I'll be a little quick about this unless there's I assume if there's some people here very much into machine learning, you'll stop me and ask me more. If not, then I'll go quickly through it. This is a particular kind of architecture that's pretty widely used for neural networks where called a UNet, where I take the field and I continually train a net on successively more and more coarse-grained versions of the flow, and I save all these networks and I get some cross-correlation between them. Let me skip that part if I don't get any questions about it and just say there's a neural net that's trained on this, and here's an example from that same simulation, the channel simulation, which is still kind of boring compared to the ocean. Sea surface height, actual vorticity, the neural network predicted vorticity, and the geostrophic vorticity. So this is like the plot I showed before, only a little bit bigger, and now you know what these mean. And so here is the CNN predicted version of the true joint PDF. Looks pretty good compared to the Laplacian. To get vorticity from geostrophy, you just take the Laplacian of the height field. So that, looks better, right? That's all you should get from that. So you can make some improvement there. It looks a little worse when you get divergence, but the geostrophic part I would get no divergence from at all. So the CNN is at least giving me now some direct estimate of the divergence. So this is a long way from SWOT, but you can start to see the idea now here, right? So you've got this statistical method that allows you to infer something, and you can't use geostrophy, so maybe we can train a neural network if we know the truth. But you can't really feed this into SWOT yet. There's a whole bunch of other problems before we get to being able to use this. And the other part is the wave stuff, which I skipped over. Okay. So how bad am I on time? Pretty bad. How much should I? What do you normally do? Do you guys just go on for? Should I stop now? Should I stop in 5 minutes?
With a stick in 5 minutes.
Okay. All right.
People might have to leave.
Okay. I won't spend a long time. Let me just say, so now I'm going to jump to another simulation. So maybe some people know there's this Herculean kind of simulation. It's part of the ECHO suite, state estimate ECHO. You guys know what ECHO is? ECCO, estimating ocean circulation. So it's MIT, NASA-run thing. There's many model simulations that use observation. So it's somehow a data assimilated, a particular method of data assimilation to produce a state estimate for the ocean. They have one branch of this that went to super high resolution that's considered, that we think of as a submesoscale, sort of a submesoscale state estimate, meaning it's not like a climatology. So they spun stuff up successfully, and this simulation was run globally for 1 full year at 2 kilometer resolution with MIT GCM, 90 vertical levels. There are 17 tide modes in it, high frequency winds, 6 hourly winds, high frequency, so it's all from atmospheric reanalysis. When people do things like they've done, kind of put fake gliders into this simulation in different regions where we have actual observations compared to the spectrum of internal waves, and in fact it does a really good job. So all this is to say it's a pretty amazing simulation. It's enormous. The output is very difficult to deal with because it's so big. It sits on an ASIC supercomputer, but it's really great. It's kind of developed in part for SWOTs. It's basically if you can think of it as something that's got most of the stuff we would see at these scales in it, and so you can play with it like that. What I want to show you here, so you can see this is South Africa, Angolas current, so super energetic region there. It's a little less energetic there, and then there's this region out here that's quite unenergetic. This is the southern hemisphere summer. Anybody know the difference between? I don't know the background of everybody here, so anything about the difference between how much internal wave energy you would see at the surface of the ocean in the summer versus the winter? You know? It's okay. Yeah, it's not a test. I'm just curious too. But you tend to see a lot more internal wave activity near the surface in the summer when you have a thin mixed layer and you have some high frequency winds. That thinness of the mixed layer will amplify the effect of the internal waves on the sea surface height. So in the summer, you tend to have more contamination with waves, which is interesting. You would think a thinner mixed layer would make things easier. In some ways, it makes it harder for SWOT. Okay. Anyway, so this is, but now, so you're used to looking at these plots. And if you look at the middle region here, you'll see that it kind of looks just like the other cases, right? The same kind of dog-eared, one floppy dog ear on the left and the perky ear on the right. And the vorticity divergence looks a lot like the original one, right? So it looks like that's like a very submesoscale rich area. If I look over here, I see something entirely different. This little egg shape with very low vorticity, kind of symmetric, higher strain than vorticity. And the divergence vorticity also, low vorticity, but the divergence is on this axis, so a lot of divergence, but not much vorticity. And over here on the right, you see something where there's kind of a mix of the two. You see the kind of egg feature in the middle, and then that spongy stuff there. So what you maybe And guess what that is after I gave you why do those look so different? So, again, the pictures here are different. So this is that same region on the left from the kind of super region in the South Atlantic. This is a simulation, so there's some code by Jeffrey Early. So it's basically it's all linear superposition of internal waves. So in this simulation, you take the stratification from the region of interest, and you assume a Garrett-Monk spectrum, and you make a whole bunch of fake waves, just linear superposition of waves, and then you could sample it just exactly as if you could sample the surface of this simulation. So basically, those are the joint PDFs of a fake flow that's nothing but a superposition of a bunch of internal waves. And you get almost the same features. What you maybe know from internal waves, I'll show you this on the right, is that they tend to have not zero vorticity, but less vorticity. They have divergence, and they might not have known they have strain, but they have a lot of strain. And so very likely that stuff that you're seeing over there is just waves. And if you go back and look at this, it means this region over here is, in some regions, you've got both things going on. So an interesting thing about the wave part, so this is just to remind you how that works. So for a plane wave, you should end up with the vorticity over divergence goes like F over omega. And remember, the minimum omega for gravity wave is F. And so, for higher frequencies, you end up getting very small vorticity, but you get similar. And likewise, for balanced flow, you get small divergence. I'm not going to emphasize that too much. Okay. One other thing I wanted to say. That's it. Does that make sense?
What does it look like in the winter?
I wish I could tell you. We haven't. So one of the reasons this particular region we analyzed, it came back to the fact that I mentioned how enormous this data set is. There was a target of opportunity that's going to be relevant for the next slide too, to use this one part of the surface output from this LLC 4320 simulation, this enormous simulation that would happen to be in the summer near the Agulhas current. That's what we had, and then so we've spent a lot of time looking at that. It's because it's sort of the data we had on hand. So I think I can't tell you exactly what it looks like in the winter right now. I might in someplace else, but if you ask me later, I can show you. Okay, so I think I kind of better. This is too much to explain, but basically one thing we want to do is figure out how can you take this enormous simulation where you have access to everything. Important point to know is that even if I have this enormous, beautiful simulation with all these parts of the flow that you expect, waves, vortices, submesoscale stuff, in fact, extracting the waves and the non-wave stuff is still challenging. In fact, that's a very difficult problem. And there's a whole approach developed by Calvin Shakespeare called Lagrangian filtering, where you seed a flow with gazillions of particles. You let these particles go, you move them backwards in time, and then you move into the Lagrangian frame and you do some low-pass filtering, and then you map it back onto the original flow, all to remove the wave part. Huge thing that I'm glossing over. There's a huge amount of work that Spencer Jones did to create a Lagrangian filtered background flow so we would have a wave-free truth simulation on which to train. Unfortunately, it was only part of a. Actually, I misspoke. Sorry. For this is the winter. The other part was the summer, but we don't have the Lagrangian filtered stuff for the summer when we would really need it because there's more waves. Okay, I think I'm going to end up going a little bit too fast here. I want to cut to the end here because I don't want to keep you. Let me just say that we tried to learn, I'll take one more cool idea from all of this and this approach. So this is from the winter Agulhas current region. And we trained the same kind of neural network to try to filter out the waves and to get that balance flow. The same kind of network I showed you before for the simpler simulation. And what is interesting is that if I try to train this to get the vorticity, it doesn't do a great job for vorticity. Should I explain this? what I'm trying to say is that if I try to train the neural network specifically to learn the wave divergence, and I keep training it with more and more and more data, the ability for it to see the divergence due to a wave gets worse and worse. And that's partly because the wave signals, so you know what, if you just know like almost nothing about inertia-gravity waves, you probably know even from shallow water that there's two wave modes. Plus, you know, you get it's omega squared is equal to f squared plus, you know, k squared deformation, wave number squared. And if you take the square root, you get two roots, right? And if I compute the vorticity, strain, and divergence from the plane wave polarization relationships, the vorticity and the strain, omega shows up in some way where it doesn't matter which sign, you're going to get the same amount. But the divergence, the reason I wrote this polarization relationship down for a shallow water divergence is the omega sits out front, like that raw. So it means if you have a bunch of random waves, an equal number and a random source, then you're likely to have equal numbers of positive branch and negative branch waves. And so if you think of the divergence then, that thing is going, if you start to average a lot, it's going to end up looking like random noise, is what I'm trying to say. I'm doing a terrible job at the end here. I hope you remember the good parts, but that in fact we try to train this neural network to learn divergence, which is going to have both the balanced ageostrophic stuff and the waves. As you keep training it, it ends up just picking out the part we want because the wave part looks like random noise. And this was kind of the important discovery we made that we think, you know, is going to have usefulness with actual SWOT. The basic idea is that the true filtered here, meaning for, in this predicted filtered case, I'm forgetting what I did here. Let me just stick with that. So I'll answer this if somebody asks me a question. And actually, the last slide is going to be my summary slide, but let me not even look at that and just tell you the things we're doing now. So this is where we are with the tools we have, and now we're trying to look at SWOT. And so we had a long gap on a postdoc, and now that's it. So we've just now started to actually look at the California current region with SWOT data and trying to figure out to transfer learn networks that are trained on this simulation to actual SWOT data. And by taking simulation and sampling it the way SWOT samples it, and adding SST and figure out how to remove cloud stuff. And so it's a big pain, but we're getting started on this last step. I'll stop there.
So Shafer,
wait, I will come with the microphone.
Before we talk, so what is the plan? In how long can we hope to see some velocity estimate from SWOT?
So if you can see them now. In fact, one of the things is if you're
talking about a product that will be used by one of the groups, right, from the team, what is the plan?
So there's different things going on. In fact, so there are, if you grab, you know, the L3 product, it will give you Laplacian of the sea surface height, as they call it, the vorticity. It's a little bit dangerous internally because it's going to have errors in it if you look at small enough scale. So you have to use the data with caution because not everyone is sort of aware of some of the issues I'm telling you about, even on the science team, although we talk about it, try to show it. There are also efforts, actually, Francisco did video, and so there's the whole Kness side too, right? And they are, one thing you can do immediately on the deterministic side is simply use cyclogeostrophic balance. So if you don't know what that is, you go back to your textbook and you figure out how can I just add, it's still a deterministic method that I can take sea surface height pressure and get an estimate of the velocities. It works specifically for a vortex, and it will give you, it'll include the centripetal force term, and it will give you a slightly better estimate. And it's still a little, we're kind of I'm now on the edge of what's available. I don't think that actually exists in any of the products, but there are people doing that. That won't help you with the fronts, right? So nobody right now has produced anything that's in the product that will tell you anything about the fronty part, and that's our goal. So when you ask that question, it's like, how long is it going to take us to give them something that can be used? I don't know. It's a pretty messy problem, so it's aspirational. 2 years.
Yes. You're talking before about how you're training, and instead of training on to reproduce the velocities, you actually train on vorticity and strain, right?
Right.
Okay.
Yeah.
I mean, that's cool. I understand the rationale why you explained, like you're basically skipping a step and that's making noise. But can you calculate transport then? If you don't have U and V?
Well, so from the divergence. So when I say transport, you're right. If I think about just vertical transport, there's still a little more to do there, right? So the vertical transport, if I don't know, I'm still going to have to use something about the information in depth. So if I have horizontal divergence, that's dWdz.
Right, but you trained on vorticity and divergence, or vorticity and strain?
All three.
Oh, okay, all three.
Yeah.
Right. So okay, I see. Now I understand. So if you have divergence, it's one.
So I have all this, but you're right. I don't really from that have direct information about the flow at depth. That's another place where there's more work to do. So in my fantasy is that in order to get all this to work right, that we started the machine learning part going to be the part that mostly helps us to filter the wave part out, and that I sort of hope as a GFD person that it is necessary to build in some of the physics of submesoscale and some kind of balanced model to allow us to get a better estimate of the vertical velocity. So I need some kind of mathematical model to take that horizontal divergence, converge it to the surface, and figure out exactly how it varies in depth and what's going to really go down, right? So,
Okay.
Yeah.
Okay.
Thank you for the talk. So I was wondering in your first part, so you say this Submesoscale genesis. So this mesoscale process, for example, mesoscale straightening are more important now is local Submesoscale or more important?
So this, similar to what Lisa was asking, both are important. So for the vertical transport, the new submesoscale stuff, the first part, my goal was to show that if I have 20 kilometer simulation with just mesoscale, I will get some vertical transport, for sure. Stuff will go down. If I start to introduce these new scales, the submesoscales, a lot more tracer goes down in the same period of time. You're increasing the rate of downward transport of tracer. So, and then the question is that because the submesoscales through an energetic cascade change the mesoscales, or is this small submesoscale features doing the fluxing themselves? The answer it seemed to be that the small stuff is actually doing a lot of direct flux. These new, fast, small fronts that form have deep vertical structures that puncture through the mixed layer and take stuff down. Now, then you can ask, so there I'm saying that both are important, but the new submesoscale stuff is important and you have to, resolve it. The question of the mesoscale part is you won't get those things, if you're thinking about a simulation, you won't get them unless you have mesoscale strain or something to set off phrynogenesis. So you need all of it. Yeah, so.
Okay, final question from Lisa. I think we need to get out of here because the biologists will come.
Okay. Yeah, I guess a question leading on from that. So with a lot of people when they talk about submesoscale vortices, they're thinking of mixed layer instabilities, right? So one of the things we're thinking about, for example, in our Cape Basin experiment is, do we need to care about the mixed layer instabilities and the kind of fluxes that they might be carrying? Or are we going to be okay just thinking about the mesoscale stirring and the frontogenesis from that and the fluxes that they're carrying? You see what I mean? So I guess that was why I was kind of interested in separating these two. So I guess a question would be, like, in your simulation, you know, have you looked at any of that, like in terms of whether you vary the mixed layer depth, whether you have strong mixed layer instabilities or not, or whether it's mostly generated by the mesoscale strain field?
In both simulations I showed, once you get to at the high resolution end of the first simulation, and of course in LLC, there's definitely there's mixed layer instability all over. Mixed layer instability tends to happen, you have more of it in the winter when the mixed layers are deeper and there's more potential energy in the mixed layer. And so it's this little baroclinic instability with an effective deformation scale of about 1 kilometer. And you know, it's going to produce vortices, but the thing is, it's an energy source. The instability isn't so much what you see. You see the whole, you know, zoo of things you see that include filaments and fronts and strong cyclones are generated by, that's part of their source. It's not the only source, right? You're introducing a new source. I think you just have to separate, there's two things. There's sources of energy, and then there's what happens to it, right? And so at these scales, you said you think most people say submesoscale is this mixed layer instability. I wouldn't agree with that. I would say that that's a new submesoscale instability that happens, but in fact the submesoscale, I would say, is all of the features, wherever they came from, that are, you know, kind of approaching order 1 Rossby number and, you know, lower Richardson number and things like this. So they're still rotation that's having some effect on them, but it's kind of losing control and new stuff is happening too, right? So,
and it's kind of super anisotropic.
Yes.
It's got these long, skinny.
Yeah, the fronts are very anisotropic, and there's an asymmetry too, and the rigidity. Yeah. I don't know if that fully answers it.
Thank you.
Okay, thank you very much. Thank you all for coming. Come again on Wednesday for Victoria Schönwald's 1 hour seminar, and next Friday we have 3 OCE student seminars here.